Thank you, guys. This Congress has been a real experience. This was my first one, so it's great to be here as a presenter for the very first time, too. So we are both researchers from TU Munich. We are doing PhD, and this is the topic that we have been looking at for the last 3 years. So briefly, what this talk is going to cover, we'll tell you what our motivation is, why we care about this technology, what this technology actually is. We will talk about Zen, we will show you demos, but really the three concepts that we will try to focus on in this talk is isolation, interpretation, and interposition. After we cover the basics, we will look at cloud security and how this technology applies to cloud security and discuss open problems. And this will lead the discussion into kernel code and code integrity, and that's where Tom is going to talk to you about. And then we'll have some conclusions. So really our motivation has been looking at malware collection, malware analysis, and using virtualization and virtual machines to do that. We've also been looking at intrusion detection and intrusion prevention. I was actually part of a DARPA cyber fast track project last year that looked at that for 7 months, and we created a prototype that we will actually show today. But the technology is also applicable to debugging and, more importantly, stealthy debugging using virtual machines. And of course, cloud security is a big part of that, as the entire cloud is based on virtual machines. But the upcoming things are mobile security and using the ARM processors that are in your cell phones to use this technology to provide some sort of protections against malware. Which is not our motivation, is to do DRM and espionage and stealth rootkits, but this technology is also very applicable to that. But we are really interested in the defense side. So you heard a lot about hacking. This talk is not about hacking, this is about protection. So when you have virtual machines and you need to tell what's happening in a virtual machine, or you need to control it even, the common approaches that you have today is that you install something in it, right? You have VirtualBox, you install VirtualBox tools. You have VMware, you install VMware tools. You have Zen, you install the Zen tools, which is very easy to implement and convenient. It can sometimes use shared memory or just most simply just use the network to communicate with your server outside. You can also use network monitors, Snort or whatever IDS systems you have. Which is better than ingest agents, which really have no isolation, right? You're running in the virtual machine. Network monitors have this isolation that they're outside of the machine. So it's more protected against attacks from within the same VM, but at the same time, you lose context. You look at the network, you see very limited information about what is actually happening within that virtual machine, especially if the traffic is encrypted. There are some steps into using live forensics on virtual machines or on physical machines even, where you can just scan the memory, which has isolation and context, but you really just have a passive view into the system. So all of these are valid approaches, but they all have their limitations. And this is where VMI really comes into play. And the basic idea behind VMI is that you look at the virtual hardware of the system, and just by looking at that, you try to understand and reconstruct what is happening within. In that sense, it's very similar to deep packet inspection, where you're looking at packets and you try to reconstruct what's happening within the operating system. And you need to have some understanding of what operating system is running within that virtual machine, or if you're doing deep packet inspection, which operating system segmented the packets to be able to reconstruct it. And for VMI, really the 3 points that we want is isolation, interpretation, and interposition, in which in isolation I mean that you have some sort of increased resiliency against attacks. And you also have complete view of the system. You have access to everything that that system is doing. And since you are in a more privileged level of the system, you can even interpose yourself into the execution of that machine. So we're going to look at these 3 things. So first, isolation. This is why we are really moving things out from a virtual machine and not having ingest agents, is because if you run the code outside, you can avoid ingest hooks, which is the most common attack vector on anything that you run within that machine. That makes tampering it harder because you have isolation provided by the hypervisor. Of course, that depends on how good your hypervisor is and how hard it is to break out from the virtual machine. But provided your hypervisor is secure and your hardware is good, then you have increased trust in the code is going to do what you want because it's in a protected region. By doing this, you also gain some performance because instead of having to deploy like an antivirus software in every virtual machine that you want to protect, you can just have one antivirus software that just protects all of your virtual machines. In that sense, you can avoid things like the antivirus storm where all of your antivirus scans kick in at the same time on your virtual machines and just kill the hardware. So interpretation is a very critical thing because you really want to understand what's happening within that machine. And with VMI, we have a very heavy focus on memory, because memory is really the common point of all the hardware that system is using. But we, of course, also have access to the CPU registers, the disk, and the network, so those can come in handy as well. But we're really going to be focusing on memory. The reconstruction of the state, though, even from memory, is really hard, and there are many problems with it, and mostly because of complexity. You look into a virtual machine, and it probably has Linux running or Windows running, and that's a large piece of software. Trying to understand what that large piece of software is doing just by looking at the virtual hardware is hard, and in the case of Windows, you don't really have access to the source code, so you really have to reverse engineer a lot of the things. And even though your code is running outside of the virtual machine, the data that code is interacting with is still potentially tampered. So we have a dilemma of what data can be trusted in that machine. But let's start at the beginning. So if you're looking at the memory, what you see with virtual machine introspection is physical memory. But of course, that's not what the operating system is using. It's using paging and virtual memory, which has been around for a long time. And the basic idea is that the operating system sets up the page tables, and the hardware walks these page tables when it needs to translate a virtual to a physical address. So it's a nice interface between hardware and software, where software provides the data and the hardware actually walks it. The problem with this very basic thing already is that, well, we have a bunch of different paging systems. So we have the 32-bit paging and 2 extensions to that, and then we have the 64-bit paging. So all right, so now we have to reconstruct all of these paging mechanisms and emulate it, what the hardware would do. So that part is fine, that is defined in the Intel manual, that should be straightforward, except there are 3 bits that the Intel manual says that are up to the operating system to decide how it uses. And Windows does actually use these bits, at least 2 of them, which means that we have a difference between which operating system is actually running, how these page tables look, and what we can get from memory. So for example, volatility has this line when it does a translation that looks at these software-defined bits in the page table entries that says that if the 11th bit is set but the 10th bit isn't, then that page is present in memory. And they do that for every translation, even if the guest is actually Linux, which is of course incorrect. So this is of course not a big problem, because, oh, okay, we need to understand that we are looking at Linux and not do that. But already shows that accurate reconstruction is complex and you can easily miss things. And this is still the case with volatility. There are, of course, other problems with memory, like if memory is paged out, then you don't have access to it directly. But we have access to the disk, so now we have to look for the swap file and reconstruct the swap file, which is, again, totally dependent on the operating system on how it's implemented, which just adds more complexity on top of that. So with Zen, fortunately, we can avoid some of that complexity. For example, now we can inject page faults from the hypervisor to have the in-guest operating system bring those memory pages back from disk, so we don't have to understand the file system and the swap file. But of course, that takes time because the virtual machine has to execute to bring that back, and it's only going to be available in the next release of Zen. But it's progress. Some other problems with paging is that you need to find the page tables. And the way forensics tools find the page tables in memory is by really just having a signature that they scan for. So in this code segment here, we have, again, volatility, which defines that 4 bytes there, which is the signature for scanning for page tables. But that's actually just the signature for a process. In fact, it's just part of a header before a process in memory. And of course, that's not very robust. But with VMI, we can do a little better. We have access to the registers, and we can just read out the CR3 register from the virtual machine and just use that for translation. So VMI has advantages over just raw memory forensics. After we have been able to translate virtual to physical addresses, of course, we need to understand the kernel and reconstruct what the kernel sees and what the kernel does, which really requires debug information. And Microsoft gives that debug information for free, but of course, the format is proprietary. It's the PDB format, which fortunately over the years has been slowly reverse engineered, but it's a pain to work with. But recently, Recall, which is a fork of volatility by Google, really now nicely supports it, where you take this debug information from Microsoft and just dump it into JSON files. So with Microsoft, this is actually, and with Windows, this is actually quite nice. This is very workable. With Linux, this is of course a bit more problematic because we have a ton of different kernels. So even if you're not taking into account your custom compiled kernel, even if you just have stock Ubuntu kernels, there is really no cross-distro central repository that you can get these debug information from. Every distribution has its own. Maybe they do have it. For old distribution, it's probably gone. So having that debug information is not as easy as on Microsoft, where they just have a very nice central repository. So there is some work in that sense to have a central place where you can grab that debug information, and that's Fedora Dark Server. But it's not really used. I mean, how many people have even heard of it? I don't see any hands, right? But there are at least some initiatives in that direction. Going back to scanning, so even if you have the debug information, you need to find those data structures that you care about, right? You want to find the data that you're interested in. So you need to find first the kernel, and then the processes and files and whatever else you are looking for. And on Windows, at least, this is done by looking for pool-tech headers, which is essentially just a debugging header attached to memory allocations that Windows does when it allocates a file object, for example. And very similarly to the scan that we saw before, these are usually 4-byte signatures that you can scan for. But the problem with that is that you have a lot of them, and you don't know which one is valid and which one isn't, because you have partial structures in memory and old structures in memory, and then you just have false positives because you are scanning for 4 characters in memory, and you're going to have a lot of that. And really, memory doesn't get reset. So if you free a structure, it's not like it's magically disappeared from memory. It's still going to be there. Just the operating system treats it as it's not there anymore, but it's really still in memory. So you need to have more heuristics to validate those hits. So now you have even more complexity in trying to interpret which data is valid and which one isn't. And that just makes everything more fragile. And of course, people have discovered that this is fragile. So in 2012, there was a paper about 1-byte modification, which just broke finding the page tables, and then volatility would just give up because it can't translate virtual to physical memory. But this year, earlier, there was another talk about just adding a ton of fake signatures, and then volatility will throw up as well because it can't tell which one is real, and then you have to go through by hand, and that's really not a feasible approach. And that just really highlights that we have fundamental problems with trusting the data, and we don't have a good way to validate which data structures are valid from what we find through scans. And that's where interposition becomes critical, because if you know the execution flow of the system, and you can trap at specific locations, you know what state the system is in, and then you can avoid scanning. So for example, instead of having to search for the KDebug structure, which forensics tools use to map out some basic structures, we can just use the VCP registers, and we can automatically find the kernel. And since we use the debug data, we don't have to use the in-memory debug data. We can just use the one that we pre-generated, and then we have complete map of the kernel. Furthermore, the heap allocations that we used before with forensics tools to find files and whatnot can be trapped automatically when the kernel actually allocates something on the heap. And what's great is there is actually native support built into Zen, so you don't have to custom patch some weird hypervisor. You can just use what's already provided. And this is great because this was actually designed for debugging, but it's really unknown, and there is not many documentation on it. And if you try to even read the Zen API, it's not going to tell you much. So you really need to look at some sample codes that are hidden within the Zen source, but it's there. So let's look at what I'm actually talking about. So this is not a live demo, I pre-recorded it, but for all intents and purposes, this will be good. So I'm running on Zen 4.4, and I have two VMs running, DOM0 and Windows 7, 32-bit. And I can list all the processes that are running on the system. This is very similar to how forensics tools do it, so that works. And you can see that I see more processes running than what task manager tells us in Windows. There are the kernel modules, which show up for NTOS kernel.exe. So you can tell what's loaded in memory for that machine. But these are all using the kernel internal data structures, which you may not trust necessarily. So now what we see here is actually the live execution of the Windows kernel, where I trapped all internal system functions that result from system calls. So these are not the system calls themselves that I'm catching, but the functions that are being called from the system calls. And as you can see, there's a lot of things happening within Windows, even if I'm not doing anything, right? So it's impossible to see what's happening, so I just dump it into a screen log so I can grab through the live output. So these are actually the functions that are being called, if you can catch some of them, but I mean, I'm not doing anything, and there's a ton of them being called all the time. But this gets you an idea that you can actually jump into the execution of the system and see what's going on. And if any of these functions you have a deeper interest in, you can actually look at them. And for example, one of the functions I'm trapping is the heap allocation function, where I can check what structures Windows is actually requesting to be allocated. And heap allocations, of course, are very much in the fast path of the system. So if I just move the mouse around, you see a ton of I/O structures being constantly allocated on the system. And that's just by moving the mouse. Now, if we have deeper interest in some of those structures that are being allocated, we can do that as well. So for example, if I want to check what files are being accessed by Windows, I can do that just by watching what objects are allocated on the heap. And I just clicked on some random personalization, and these are all the files that Windows accesses in the background that I'm not even doing anything, this is just still loading, right? And it's still going, all right. So if you want to debug an operating system, this is really great because you have full understanding of what it's doing. And just to show you that this is actually what's happening, I just create a document here on the desktop. And as you can see, there is still a lot of things happening, so I don't even necessarily see the file that I created. So actually, I'm just going to cat through that screen log to see if the file was actually in there that I created. And yes, it's there. And it's actually test.txt.txt because Windows automatically adds the extension for me. So I did not know that. So the way this works is actually using 4 types of events on Zen. Unfortunately, this is for Intel only, but that's good enough. The first type is move to CR register events. So this is, there are 3 control registers the operating system uses to define various features. The CR3 is, of course, holds the page table address that is used for the current executing processes, virtual to physical translation. CR0 and CR4 holds various options, can be used to flush TLB, and we can trap every time those registers change. So we have an understanding when a new process gets scheduled in the operating system, so that's great. The second most important one that I used here is debugging breakpoints. So these are just really the debugging breakpoints that you would use if you run GDB or only debug, which is the int3 instruction, hex cc opcode. And you can just write that anywhere in the kernel code pages, and it will trap. And you can actually configure the virtual machine to trap into the hypervisor when such a breakpoint happens. So that's pretty great. The other event type is via the EPT violations, which is the extended page tables, where we actually have another whole other set of page tables that are maintained by the hypervisor that maps what memory is allocated for that virtual machine. And before EPT, this was done via the shadow page tables, but now with EPT, this is all managed by the hardware. But the good thing is that you can set different permissions in the EPT tables than what the operating system sets in the virtual machine. So you can actually trap various accesses, read, write, or execute instruction fetches from memory. And then the fourth one, which is also critical, is the monitor trap flag single stepping, which is an invisible single stepping feature built into Intel processors now, where you can actually single step a virtual machine without having anything within that machine knowing that it's being single stepped. Well, there is a bunch of other features that Intel now allows you to trap on, but these are basically the four ones that Zen currently supports. But as you can see, this is already pretty cool. Like, you can do a lot of with these four types. As I said, using the Zen API is really not very nice, and it's kind of hard to actually wrap your head around how things go together. But fortunately, you don't have to. So the way I implemented this system is using libvmi, which is a hypervisor agnostic C library that we have been working with and actually extending heavily, which is a wrapper API around Zen, KVM, or even if you have raw file dumps, you can do introspection on. And it supports all the paging that is out there. Plus, I recently added ARM support to it, so you can actually do introspection on Android devices, for example. But for now, it's basically Windows and Linux. It has a Python interface. And really the idea here is that you write code once using libvmi, and then if you switch the hypervisor underneath, it's not going to matter as long as the drivers are set up properly within libvmi, and then you write code once and it's good to go. You can use it to read and write into memory, and it has wrapper around Zen events. So it's actually intuitive on how you need to do like single stepping and setting up things. And it's open source. So it's LGPL, so you are free to use it with any project that you want to implement. So a little bit more details about how the actual tracing happened that we just saw is I injected a breakpoint into the xallocate pull width tag, which is the heap allocation function. But of course, when that function is called, the memory is still not allocated. We need to catch when that function finished. So we need to extract the return address from the stack, trap that as well. When the return address is hit, then we can actually extract the address where the memory got allocated. The trick here is that there can be actually a bunch of different threads calling this function, and while you're in this function, it can be context switched, so you need to keep track of all the callers of which ones are actually active. That when it returns, you know that, okay, this was the structure that I was actually waiting for. And then you know where that structure is allocated, but it's of course at that point is just a memory address. The structure is not initialized or anything. So now you have to really watch that memory region as it's first like being zeroed out and then slowly updated as the operating system fills in all the headers and the information that we really care about. So for example, here we would care about the access type to the file and the file name. So we just set up the EPT traps to monitor as that page is being updated. But then, of course, this traps the entire page that that structure is on. So you're going to have unrelated write events. So there is even more logic in there, and that adds overhead. But as you could see, it was quite responsive. You could move the mouse around and interact with the virtual machine, so it's not too bad. What's really cool about, though, about heap tracing is that some basic kernel rootkit mechanisms can be really sidestepped. So for example, direct kernel object manipulation, which has been around for 10 years, is the idea that you can break the integrity of kernel data structures without actually affecting the execution of the system. Where you would have, for example, a process, in this case in the middle, that doesn't want to be found by task manager or by the user. And what it would do is unhook itself from that process list that I actually showed you in the beginning, where I listed the running processes. And that's just a linked list, so if you just switch the pointers out, the structure will be still in memory, but you won't be able to find it through the linked list. But of course, now with heap tracing, we know exactly where every structure is allocated without having to walk the linked list, so who cares if it's unhooked from here? I know exactly where in memory that process structure was allocated, and that increases the trust in the data. And furthermore, I can do some type of cross-validation to see, like, okay, I know this structure got allocated at this address, but it's not showing up in the linked list. Well, that's probably some rootkit. So let's look at another demo. Here are all the running processes, and of course I have paint running. I cut down the output so we can actually see what's happening here. And what I'm trying to show you here is that you can really catch any event that you want. So in this time, I wanted to catch when that file gets deleted, but before it actually got deleted. And what I did is I actually fired up volatility and dumped that file from memory before the operating system was actually able to erase it. So now it's in the temp folder, and there you go. It's actually extracted into the control domain. So you really have full access to that virtual machine, and you can reconstruct everything that's happening within, and even extract files that were, in this example, closed and deleted, but I was able to extract it from memory because Windows doesn't actually delete it right away. And this is very handy when you're dealing with malware, because a lot of the time what happens is that you have write caching enabled on the disk. So when you actually say save this file, Windows doesn't actually save it to the disk right away, it just queues it up and waits for a while to have enough writes buffered off, and then writes it to disk. So even if I would look at the disk after I save the file, I might not even find it because it's still in memory. And for malware, this is actually usually the case, because you have temporary files that the malware dropper extracts and then loads into memory and then cleans up after himself. And you really need to catch the delete events, otherwise that memory region can get recycled. So for example, what I was doing first is I was just running some malware samples and pausing the VM when I saw some files that were interesting. And then I tried to go there with volatility and dump that file, but of course the memory already got recycled. So there is really a very short time frame where you can actually catch these files. So interposition is really critical if you want to do malware analysis. Let's look at another demo. Demos are fun. So this time I have Windows 7 64-bit. There is some debug information about it, but it's 64-bit Windows 7. And there are all the processes running. And as you can see, there is Task Manager 2364. And what I'm going to show in this demo is how you can actually take full control of that virtual machine, not just extract files and monitor passively what's happening. So for example, what I'm going to do here is actually hijack the Task Manager to start up Calculator for me within the virtual machine, which is quite great because I didn't have to install any custom software within that virtual machine to take control of that. I just need any process that is executing within that virtual machine, and I can do whatever I want. No passwords asked, no username. Really, you have full control, right? That's what being in a more privileged level of the system actually means. And yes, you can fire up command.exe and pass whatever arguments you want to it. And as you can see, I actually get the return value as well, so I know what the PID of the process that got created is. So if you want to execute some function within that virtual machine, you can actually extract the output of that, and then you can just pipe this together. So you have like an external shell for that virtual machine effectively. So now what I'm going to do is actually just fire up Internet Explorer and send it to some website of my choice. And there we go. The virtual machine just happily does that, and it's pretty much instantaneous. So I really can control what that virtual machine is doing. So if you're like a sysadmin, this is great. You can install software within the virtual machine, close processes, really whatever you want. So all the demos that I showed you are actually part of a malware analysis system that I built for my PhD, which is, as I said, built on Zenlib VMI, volatility and recall, and it's released for free for you. So all of these demos and tools are now yours to play with. Thank you. And again, the important thing here is that for malware analysis, you really don't want to have anything identifiable within the virtual machine that you are running in, because that's what malware usually looks for. So if you have no in-guest agents, you don't have any in-guest artifacts that malware can look for, and then you have a more stealthy environment to do your analysis in. And of course, you can extract all the temporal files that you would otherwise miss. And OpenOffice just crashed. All right. Doesn't really like embedded demos. Another tool that I wanted to bring your attention to, which is really just fresh out of the oven, is debugger integration. So as I said, all of the features built into Zen were really designed for debugging, so why not use some of your favorite debuggers, in this case, GDB. So this should be online by now. I haven't actually had a chance to test it, but this has just been released. So this allows for stealthy debugging using the hypervisor, and you can really debug your operating system. So if you are developing a kernel driver or whatever, this is really handy. And of course, we can add WinDebugger integration, which is coming next. So go check this one out too. So let's go back to isolation real quick. So now what we did actually is we moved a lot of the security stack out of the virtual machine, and we can do a lot of with that. But what that really just achieves is just moving the target. Exploit is getting harder because you have hypervisor-based isolation. But of course, now you're running in a more privileged part of the system. So if you actually manage to break out using some vulnerability potentially in the security tool, then you have a bigger reward. And it's not like it doesn't happen. I mean, there was just a couple weeks ago, a month ago, local privilege escalation in OSSEC, which is a host-based intrusion detection system. So it's kind of naive to think that our system wouldn't have any vulnerabilities. So why not separate the security stack into also deprivileged virtual machines? And Zen has some features to achieve that, and that's the Zen security modules. And what that allows is to really disaggregate the trusted computing base that you use with Zen. So you don't have to put the security stack within DOM0, as I did in the demos here, but you can actually create a virtual machine that has control over a set of domains that you want to protect, or just maybe a single domain that you want to protect, without affecting anything else on the system. The way it works is it creates a wrapper around hypercalls and has a policy to define how the interaction between domains can happen. This is actually a piece of software that has been contributed and maintained by the NSA and Zen. And they have a bad reputation, but in this sense, they actually do some positive work as well, because without their work, it would not be possible to do this. And as I said, what it does is actually a wraparound hypercalls, and then you have the Flask policy engine where you define which virtual machine can do what hypercall and what the target is of that hypercall is. And in that sense, it's very similar to SE Linux. You can use the same tools to define your policy, audit to allow, and check policy. And it's disabled by default, but I mean, you can recompile Zen and then have this. But really, it's only usable from Zen 4.3 and Linux 3.8. So that was actually my first patch to Linux in 3.8 when we were actually testing an early version of this system that was not merged into Zen yet. And we discovered that the Linux kernel actually did some access control checks itself to see if it is DOM0 or not. And if it wasn't DOM0, it would deny issuing the hypercalls that we needed to do this type of security. Of course, if you have XSM defining what is allowed and what isn't, you don't need the kernel to tell you that. And furthermore, that's really an arbitrary check. If you have the rights to do insert kernel modules within your kernel, then having a security check there is really not going to get you much. So my patch was really just removing that surplus check. And now with these tools, we can actually start thinking about cloud security, right? So we have a mechanism to have different security policy for different users of that cloud. And the idea would be is that we start monitoring a virtual machine before it goes live. So we have some sort of baseline of integrity that, okay, this is my base API, it hasn't been released on the net. So I start monitoring. And we can see if some critical data structures get hijacked, or maybe even the code, if there are any inline hooks being injected, we can detect that. And we can really just limit what we are trusting in the data to stuff that is bound by the hardware, because if malware changes those structures, the most that they can achieve is DOSing the system. So they probably won't touch it if they have some better use of that machine. But we are back at what data can we really trust in the system. So for example, with the events that I showed you with EPT violations, there's already some limitations in what the hardware tells us. And there are corner cases. So for example, read, modify, write instructions, which in one instruction read from memory and then write back to memory, which is usually used for mutexes and concurrency stuff. The Intel manual says that, well, it's really implementation specific whether it says the read bit. So these will always set the write bit, but whether it says the read bit, it's, well, we don't know what happens. So that's not really cool. We actually patched that in XAMPP 4.5, which will be released next month. But there are ambiguities, and there's a lot of ambiguities like that in the Intel manual. So we actually wrote a paper about collecting all of these, and these are just really some of what the limitations are. A bigger limitation is really the tagged translation look-aside buffer, which was introduced in 2008, both by Intel and AMD, which essentially caches the translation of virtual to physical addresses into a cache that you cannot query. It's really just for the hardware to speed the translation up. And now if you have a tagged TLB, that means that the page tables don't necessarily represent what translation the guest actually uses. So what we do with VMI is we look at the page tables in memory and we emulate what the hardware does, but we don't have access to this cache, which is a problem. Because with tagged TLB, the cached entries survive a VM exit VM entry, so these are actually persistent TLB entries. And that means that the rootkit potentially can muck with the page tables in the guest without actually crashing the guest, and we would have no idea what it's doing because it can set up the page table to point into some benign code region, and when we try to see what code is actually running, we see that, oh, it's calculator, it's no problem. But what the machine is actually executing is something totally different. Of course, there's some limitations to that, so depending on what hypervisor and guest operating system you're running. So for example, Zen always assigns a new tag whenever the guest schedules a new process, so you would have to do some malicious modifications to the page table essentially every time a new process is scheduled. So okay, we might be able to detect that. And Windows 7, surprisingly, is actually pretty good against this because it always flushes the global pages like very regularly. But if you're running Linux on KVM, well, this is a more realistic problem. But if you think about cloud security for a moment here, there's really no need to move everything out from the virtual machine. So with malware analysis, there was a reason, right? You don't want to have any artifacts within the guest that it can detect and shut down really quickly. But with cloud security, we want the malware to stop executing as fast as it wants, right? We don't want it to stay alive. So maybe it's enough to have some sort of securing guest agent that we can protect from the hypervisor level, but it would have better performance and better visibility into the system because it's running in the same context as the virtual machine, so the tagged TLB problem doesn't exist for in-guest agents. So that we can do some sort of hybrid approach, potentially. And this is actually where the hardware is heading. So in the upcoming Intel CPUs, there is going to be this extension called Intel VE, or it stands for virtualization exceptions, where you can actually trap the EPT violations within the guest, so you don't have to trap out all the time into the hypervisor. So you would have really better performance, and then you can do some sort of protection of that code that's running within the system. And as I showed you, you can really control what that system is doing, so you can not just control the code, but you can also control the data. So you really can achieve secure in-guest agents. Another approach would be for cloud security is to really just reduce the size of the guest operating system. There's really no reason you need a full Linux stack in your operating system that just serves Apache, right? So there are some works in that direction. So just in this Congress, we saw Mirage OS, but there is also NetBSD ROM kernels and OSV, which really just try to achieve that reduces a virtual machine into a process and then just use the hypervisor as your scheduler. Which is kind of ironic if you think about it, because processes back in the day when they were introduced, they were called virtual machines. And now we would have virtual machines becoming processes again. So we are kind of going in a loop here. But also we could try to secure the in-guest kernel, Because what we have actually been discussing thus far were the blacklist approach. We look at what malicious changes happen to the system, and we try to deny that. But that, of course, places the burden on the defender to enumerate all the possible things that could go wrong. Well, good luck trying to do that. So now I'm going to hand over to Tom to talk about the whitelist approach, which might be a better alternative.
Yeah, so if you want to verify the integrity of the system, which we have to run our ingest agents in, we have to see what the kernel is in the system and whether it's changed by malware or not. So what we propose is a whitelist approach that would allow verified changes within the system to the kernel. So for that, we need to validate and see all the changes in the system that we want to allow. So code integrity basically is assumed to be an easy thing. You have the code which from your binary, from your kernel. You hash that, and you compare the hashes. If it's matched, then the kernel or the kernel's integrity is there. But actually, Linux employs runtime patching, or runtime self-code patching, to have performance optimizations within the system. So for that, if you run a Linux kernel, you now have to differentiate between legitimate and malicious changes to your software. So there are two kinds of changes that are done by the Linux kernel. So for the one thing, there are the easy load time patching things. Yeah? The easiest thing is the relocations, or alternative instructions, which are architecture specific. So dependent on the CPU the system is running, or dependent on the hypervisor the system is running, there are different instructions patched into the code of the system. So depending on the hypervisor, for example, some function can be implemented that way or another one. So, but you can say, yeah, load time patching can be handled by loading the kernel in a secure environment on the same architecture maybe, and creating a hash, and we still have no problem. But on the other hand, we also have runtime patching employed by the kernel, which is, for example, employed for hardware hot plugging. But this has to be validated and verified continuously as the system is going on. So I want to show you two examples where this is actually applied in the current Linux kernels. So for example, SMP logs is one of those mechanisms. So currently, if you have virtualization on a system and you need scalability, the number of actual CPUs that are allocated to the virtual machine may change during runtime. So this gives a problem, because if you have a single-threaded operating system and you have logs, then you don't have to ensure atomicity of that log, because you have only one CPU anyway. This changes if you have multiple CPUs, because then you really need atomic operations. And for a performance reason, if only one CPU is present in the system, the Linux kernel does not use those atomic operations. But instead what he does is, when another CPU comes to the system, he automatically patches all these locations in its code to atomic operations, which are slower than, but required in that place. And also this mechanism can also be used to replace entire functions within the Linux kernel. It's currently not used as that, but the mechanism is basically there. And another thing where runtime patching occurs in the Linux kernel, for example, is a mechanism called jump labels, which is equally for performance reasons. So you have some checks in the Linux kernel that will be unlikely passed. So other than just checking constantly, is it an unlikely case? Is it now an unlikely case? You just patch out the jump to certain code snippets out of there. But once those functionalities are enabled, for example, by a user or by any hardware mechanism or whatever, the Linux kernel just patches the jumps into the code to the function that should be executed. And with that, we have the additional problem that we don't have only two possibilities. The patch is, the jump is there or the jump is not there. But the location where the jump points to also has to point to a location which is consistent with the entire system state. And here you have like the perfect thing for something return-oriented programming, where you just need to have an arbitrary jump within your code. So these are mechanisms that we have to defend against. And to verify that, we already heard, we have simple approaches like lock-in the kernel. Yeah, the easiest thing with the hash-based approaches, as I said, is deny all changes to the kernel code at runtime. But here we have the problem that we completely disable all of this legitimate patching approaches. And on the other hand, you also can say, well, most of the code is static, but just a couple of locations might change. But here you have an equal problem. The number of hashes that you have to maintain for every location that might change is a very large number. So you have to maintain very many hashes. And also, the Linux kernel in its current form has a problem that for some code pages, both code and data reside on the same executable page. So the kernel, for its code pages, uses large pages, which are basically 2 megabyte pages, that are used for kernel code. But on the last page, there is still some spare memory that would either be wasted, or the Linux kernel gives that to user space applications if they allocate some memory. So here we also have the problem that we don't know really, is this code, is this data, what is to verify, what should be on that page. So this is also a problem for hashing the kernel. So what we propose here is a trap and violate approach using VMI. So we know patching only happens to predefined locations. So from the binary we can derive which patching mechanisms are there, and where or at which offset in the binary the code will be patched, and also with which values under which circumstances. And for that, we can now retrace those patching mechanisms and understand what they really mean, and also see their system state, that it's consistent. And also, this fixes another problem, because the code patching is not an atomic operation. Like, for example, if you patch entire functions, that cannot be done at once. So there's always, like, between the two good states, a bad state in between, which is also good because it leads from the one to the other. So you have to have a system which is aware of all those intermediate states and can handle them appropriately. So we we propose to trap write events to kernel code, and when the kernel code is changed, you can validate that the change is not malicious, and thus provide the integrity of the running Linux kernel. So this basically now was about the integrity of the code, and with that I want to conclude. And as a summary, to say, VMI supports a wide spectrum of applications, from malware detection to cloud environments. And VMI gives us the 3: isolation, interpretation, and interposition. But depending on what you want to do with VMI, it depends on which of those 3 features you want to have most. So the pure VMI, as in isolation, is not required for all of those use cases. So you have to see whether you want to have an ingest agent, which you can secure, or if you want to have very intrusive mechanisms which make the execution of the virtual machine maybe slow. So you can have, like, the more in-depth view, the less performance, or trade between those. But as we said, the hardware support for all of these mechanisms is continuously improving and gets better there. The tools that we showed you today are open source. You can look at the websites libvmi.com, drugwoof.com, and you can find us libvmi on Freenode and our contacts respectively. After that, I just want to say thank you to all of the names here on that slide. Without those, it wouldn't be possible. And conclude our talk and be ready for all your questions.
So if you have questions, please line up on the microphones. And if you absolutely must leave the room, do it quietly. Number one.
I have a question on the runtime patching. Does your code work with the function tracer in terms of dynamic ftrace and also with the upcoming kernel feature kpatch or kcraft?
With the ftrace feature, it works. Currently, with the function tracer, with the function replacement, it does not currently work. I have not implemented that yet. And also, for the tools are open source. That last part is still to be published, but this will happen in the near future.
Okay, thanks.
Number three. Four.
Four is me. Okay,
Three.
so first,
It's me. Okay, one question. You showed this tool for this tracing of the memory states. So you mentioned that it's only supported under x86 right now. Are there plans to support ARM Xen as well at some point of time?
Yes, I am actually been working. I was hoping to get that into Zen 4.5, but unfortunately the freeze window closed just too early, so it's going to be available in Zen 4.6.
Okay, because there is this octa-core ARM platform coming up, and it would be really handy to have it on ARM as well.
Yes.
So next release, I can expect it to have these features as well.
Yes, we are working on it.
Wonderful.
A question from the internet?
Yes, we have one question on IRC. What is the easiest way installing a hypervisor in a general Linux OS? And what are the minimum hardware requirements for embedded systems with current distros?
I have been compiling Zen from source myself, but I guess you can apt-get install Zen, something of that effect. KVM is of course built into the kernel, so that's usually loaded if your hardware supports it. So usually your distribution has some built-in support for that. So.
Microphone number four.
okay, so I was first off I was trying to get into the same area as the first guy. What's the actual purpose of those tools? I mean, those tools are really cool if you want to analyze a system. You have a contained environment, and you want to you know that it was compromised, and then you want to figure out what actually went on, right? So you can analyze it dynamically and trace things. That's pretty nice. For an actual live system, everything that's coming up with live patching, like perf, like kgraph, like the others, you can't do a fingerprint for a security vulnerability that's going to happen in a year, right? So you simply cannot do a whitelist because you are in time before the fingerprint would get created.
But that's where the whitelist approach sort of comes into play. Like, you know what the good things that can happen to the kernel, so only allow the good things that you want and know about, and everything else you can flag as potentially malicious.
Right, but it means you need to update your whitelist before the cache can be updated. So you have a time.
Right, so if you deploy a very new kernel that the protection tool doesn't know about yet, then yes, that has to happen in 10.
Okay, so imagine there's a 0 day coming up, and somebody like you basically get a specially crafted kgraphed kernel module that you load to fix that kernel that thing. It's first off, it's probably tailored to you because you might actually have another security fix in your system that is just only for you. So you actually might be running a kernel that's not fingerprinted by you or by anybody else, or your host provider, your cloud provider, and then the cloud provider might not even know about that fix yet because, well, they might be in the loop after you.
Yeah, but that's a general thing. Like for the kernel integrity part that I showed, that's very, very kernel specific. Like you need to know exactly which kernel is running on the system with everything. You have to have the binaries, and currently we extract all of the information for our verification or validation out of the binaries. So if you as the cloud provider don't know what's in that system, you can't do that anyway. But you're also not supposed to do, because if you were supposed to do that, you would know about the patch that is in the system. And if you can also take, like, this is the kernel code that we are running, and these are the patches that we are applied. From that, we can build like the ground truth and match it against what's in the system.
So my main point is, I don't think cloud is the right term in this case. This really is an awesome thing for embedded projects where you control the whole stack. As soon as you have different tenants doing different things, things fall apart because not everybody has knowledge of everything left and right.
And also, this is also not only like for real malware detection. Like from the beginning, you have a system you think is clean, and if you work with a system, you have the different tools that with which you can look at the system. And once one of the system reports any funny things about the system, you definitely have to investigate further. So you don't have all our systems running like with the most details viewed about the systems, and it's also not for preventing any malicious things. Or entirely for preventing them. So it goes in the right direction, I think. But it's not a tool like that solves everything.
Just having a hard time figuring out where data is used. But so the second thing I had was on the VMIT flushing stuff. So the first generation CPUs didn't, like first generation VM capable CPUs didn't have ACIDs or anything of the likes. And performance difference between having ACIDs and not is like, what, 5%, 2%, something around that ballpark. You can just flush an every VM context switch and call it a day. Just submit a patch to KVM to enable always, to flush it always.
Right, I mean, that's always a possibility that you just disable tagging. And your problem goes away, but then you sacrifice performance. And usually,
you always sacrifice performance if you trap on every heap allocation, right?
Yeah.
So the performance really is not an argument here. If you lose 2%, you don't. The 2% is definitely a lot less than the overhead you already have.
It depends on what your security application is doing. So you might not need to hook all the fastpath functions to really protect stuff. So it really depends. As I said, you probably don't want to trap on everything, because if you have an ingest agent, then you don't need to trap. You just have something within that you protect from the outside. And for cloud applications, that's probably the way you want to go. But for malware analysis, doing something like this where you really can't trust any kernel data, that's really essential.
Okay.
Yeah.
Number one.
Are any of the large cloud providers offering malware detection service for their clients?
Not yet, but we are expecting that to happen soonish, I guess.
Number three.
You mentioned something about Android. How far we are today to use this VMI and the system on ARM devices?
So the thing with ARM is that we have the two-stage paging, and I have the code to have that trapping mechanism working with Zen, but unfortunately that's only one part of the picture. So for all of these things that I showed here today, it really required all 4 types of trapping. For now, it's only the memory part that's functional, so there is more research need to be done on how to do single stepping and efficient trapping. So, for example, there is no breakpoint trapping on ARM, so there is some alternative that needs to be found yet, but it's still very early in the research phase. So, interestingly, the people who are looking into that mostly are Samsung, so I expect them to have some sort of security stuff that they want to sell soon. So it might be improving as well. So,
and does Xen already support full virtualization on ARM?
Yes.
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 Thank you.
So if we have no other questions, we will conclude the talk and thank Thomas and Tomasz for this very deep look at the hands of the kernel.